Hello everyone. Welcome to another episode of writing parser combinators from scratch. Let's pick up where we ended last time and let's first define what we will be parsing today. I'd like to parse operator calls. Ones you could imagine in a compiler somewhere for some kind of language or DSL. And it will be very simplified, just a number, an operator, and another number. No parentheses or nested computations, no operator precedence, just two numbers and an operator. We can define the operations right now. It will be addition, subtraction, multiplication, and division. And let's document some examples of how the input strings could look like, just to have an idea. This simple example is already enough to take us through a whirlwind tour of parser combinators that we don't yet have implemented, so it will force us to expand our library and let us think about how they work under the hood. Our example parser will need to parse the two numbers and an operator between them. A number, an unsigned integer in our case, is made of multiple digit characters. Digit characters are characters between 0 and 9. It will take those characters and try to convert them to an integer. The many combinator, which will parse one or more items, can be made with another combinator, sum, which will parse 0 or more combinators. You can imagine we would say parse one item and then parse some other items, the rest of them. The sum combinators ultimately needs to only try to parse an item, and if that doesn't work, it needs to try another alternative, which leads us to the one-off function that will let us do that. And finally, or maybe I should have started with this, the operator parser will accept one of the four operator symbols and map them, transform them to the custom type that we have defined. Let's go top down first. Let's write our example parser, and that will uncover what we need to work on next. It's going to be a number, then the operator, and then the second number. Let's make to-dos for the number and operator parsers. One will give us an integer back, and the other will give us the operator back. We can expand the operator parser right away. As we've said, it will look for one of the four symbols, each of which will correspond to its operator. You might remember from the first example that the string parser gives us an unit, an empty tuple, which is kind of useless on its own, so we will override it with the operator. Let's make a to-do for the one-off function as well, but we will keep it like that for now. And one to-do for the map function. This one is easy enough to implement right away, let's do that. It might be familiar to you, for example, from the list or maybe types, and there it works on the contents of the containers, but here it works on the result of the computation. If the original parser returns an error, we just forward that, but if we get a parsed value, we run it through the function the user gave us. That's map. Now let's look at the number parser. It will definitely do something about digits, which we can express with something like character between 0 and 9. You can see how this could be useful for other use cases, like letters. Those would be a character between A and Z, and so on. We want the number parser to parse multiple such digits, not just one, so let's wrap that in many. Many will give us one or more of these back. Let me be a little bit fancy and express this one or more promise on the type level. We will say it returns a non-empty list. where a non-empty list is an item and the rest of the items. The list on the right could be empty, but the item on the left guarantees that we have at least one of those items. Now in the number parser, once we have these digits, they are still in the string or rather character form. We need to process them and try to convert them into an integer. We first need to convert them to a string. And then we can use the function string to integer and see whether that succeeded or not. One of the functions we used but didn't define yet is endThen. Let's go implement it. It will look very similar to the map function. The only difference is in what the user provided function returns. Instead of a transform value, it returns a new parser. Once we get the initial value, we run the function to receive the new parser, and then we can run it on the rest of the string. Looking at the to-dos we have, character between will be the easiest to implement. In the standard library there's a very useful function uncons, which will give you the first character and the rest of the string, or nothing if you give it an empty string. So if we get nothing, we can fail, saying we reached the end of the string. And if we get a character back, we can check it. Is it in the bounds? If yes, return the character and the rest of the string, and if not, fail, saying that we have read a character but it wasn't one we cared about. Let's expose those helpers and try them out in the REPL. A parser for a character between 0 and 9 should be able to parse the beginning of the string and give us that first character. It will fail when it sees a letter. Let's take a look at the many parser. We are almost near the end. As previously discussed, we will parse the first item and the rest of the items and return them together in a non-empty list. Because they are not dependent on each other, we can use the pipeline pattern. Sometimes you will hear people say applicative pattern. Doing this, we have mentioned the sum parser, and this one will return 0 or more items, so the usual list is a perfect fit for that. You can imagine it will involve some kind of a loop, and in functional languages, loops are usually done with recursion. We will define the sum underscore function that will recurse on itself. It will contain a list of previously successfully parsed items, and due to how lists in Elm work, they will be in reverse, and tries to parse one more. Either it succeeds doing that, remembers the new item and repeats, or it gives up and gives us all the items gathered so far. When unsuccessful, we need to reverse the list of items before returning it. Now, how do we try parsing another item? We use the parser, and if successful, recurse. Let's expose those new functions from the module, and we will also need to fix a few typos, namely we need to use the item parser instead of parser. We can't really try them in the REPL yet, because they depend on one-off. That's our last to do. First of all, if the user gave us no parsers, let's fail straight away. And if we know we have some parsers, let's start processing them in our recursive function helper. The purpose of this whole parser, and so of this helper as well, is to stop on the first possible parser that succeeds. So we need to try the one we currently have. And if it succeeds, we are done. But if it fails, we try another one. And if that was the last one, we return the error we currently hold. But if there's more parsers to try, we recurse and try again with the rest. As usual, there's some unwrapping that we need to do because we are inside the parser function. We are not on the outside surface level combinator API. And you can see that we are giving the other parser the same original string. They will try from the same starting point as all the other alternatives before them. Let's expose everything and also fix a tiny error where I forgot to rename the helper function. Now, in our REPL, we can try things out. The number parser can parse longer numbers like 1 to 3, and we get an integer back. It doesn't care what's at the end, and if there's no digits, it will fail. The example parser, the thing we started with, should now work as well. If we give it just a number, it will fail because it expects the operator next. An empty string will not work either, we need a number, but the happy case works. A number plus a number gets parsed, a number minus a number gets parsed, and so on. If we use an unknown operator, that will fail, as will when we forget the last number. And that's really it. The main issue you might have found is that our error reporting isn't great. That could be something to look at next. Until then, happy parsing!